Okay, I think we'll get started. As I've been mentioning in the last few lectures, we're in the part of the course where at Concordia here we're doing a lot of in-class activity, so it doesn't match well with the GNL project. And this is what I was primarily referring to when in the other videos I suggest that you look at the introductory video for this course to make sure this is the right for you. But I do have some videos that cover these topics, so I'm going to splice those in here. A few things will be out of order. Mainly, we will be hearing about the concept of energy before we've actually talked about it. So if you're in the GNL Project, you're following along with the book, just keep going with the homework, but try to think about the next couple of lectures as being sort of all together as one unit, and you can come back and forth to these videos as we introduce these topics as we go. If you're at Concordia, you can, we'll be doing the in-class work, but you could use this video just for some extra. Just keep in mind that the concepts will be out of the blue. Okay, I think we'll get started. So today we're going to talk about angular momentum and specifically conservation of angular momentum. We've talked now a bit about Noether's theorem throughout the course, and this idea of invariances giving rise to conservation laws. And the last of these is rotational invariance. So physics is the same here as if we rotate, and so that invariance through Noether's theorem gives rise to conservation of angular momentum. Now we won't really be able to do the subject justice. As we progress through the curriculum, we will have specialized units in courses on angular momentum, and particularly in our mechanics courses and then in our quantum mechanics courses. So today we're just going to talk more or less an overview and primarily about rotation just in the plane. All right, so we've starting to have this catalog now of linear and rotational relationships here. So linear, distance is x usually, but we can call that s here if we're talking about arc length. And that corresponds to angle. And we have the relationship that is common throughout here, that the radius leverages that distance. So I've got a long radius and I go through an angle, I travel a bigger distance than if I have a short radius and I go through that same angle. Velocity is the rate of change of the distance, and so angular velocity is the rate of change of the angle, and again leveraged by r. And then the rate of change of velocity is acceleration, and the angular acceleration then is the rate of change of angular velocity, and again leveraged by r. The analog to mass in the rotational system we saw is moment of inertia, and the relationship here is I equals mr squared. And then where forces play the primary role in accelerating a mass in a linear space, or in linear problems, torque plays the primary role in accelerating in a rotational problem. And we have an analogous formula, F equals ma, and tau equals ia. And the relationship between tau and force is the force applied perpendicular to the lever arm is what gives rise to the torque. Now we have momentum, and we introduce here angular momentum. And then we have, how does momentum change? So this is a conservation law. We need a force acting on the system to actually change the momentum. So in the absence of forces, the external forces, so collisions can happen, anything can happen. We have conservation of momentum, as we've seen. But if we have an external force, such as an impact, then we can change the momentum. And we talked about impulses, J, and I'm taking the vector off here. The vector notation is a little awkwardness here, and we'll talk about that in just a bit. So then the impulse, the rotational impulse, which I don't know if it has a letter associated with it in a that's typically used. I'll just use J again, so an impulse can initiate a rotation. So that would be a average torque over time, and that will give rise to a change in angular momentum. Now here's this idea with the vector. We really need 3 dimensions to talk properly about angular momentum, even though if we have rotation, we can always, whatever this rotation is, we can always choose a plane so that that is rotating in, say, the XY plane. But the direction of the angular momentum is actually obtained by the cross product. And if you haven't had vector calculus yet, then this will be a little foreign to you. But the idea is that, or the result of this, is that if we're rotating, right, in any direction, I can choose a plane, and if I use my right hand and I curl my fingers in the direction of the rotation, then the angular momentum is going to be, that will give me the direction the angular momentum is pointing. So the angular momentum points perpendicular to the plane of rotation. And so you can't really technically talk about such a vector if you're living in a 2D world. So if we're stuck in a 2D space, we have to think about angular momentum a little bit differently. It's more naturally just works in 3-dimensional space as the vector cross product. Okay, well, let's derive these formulas here. These formulas that we see here. So let's first get our angular momentum here. So I'm going to take this formula here, the torque formula, and let's rearrange it and solve for acceleration. So acceleration is torque over moment of inertia. What is acceleration? Acceleration is the rate of change. Right? Acceleration is the rate of change of the angular velocity. And so I will replace this here. Now I'm going to bring the dt up here and the I over here, and I get I d omega equals tau dt. Now I'm going to look for the analog here in what we've seen before. If we have a force for a small time, and we've used, you can, if you haven't had calculus, just think of it this way, as we have before. The average force over a macroscopic time is dp, right? And you can think of this as that in the non-sort of calculus notation. Well, m's not going to change, so m can pull out, and this can be written as m dv. Now let's take this again. I'm just going to pull this down. All I'm doing here is I'm just taking this equation, flipping the left and right, and we're going to look for an analogy here now. So here and here, right? These are our rotation and linear analogies, and so there should be something that is I d omega, and that's what we will call the angular momentum, the change in angular momentum. So a torque over time, and you can think of it this way too. So torque average, delta T, is delta L, if you haven't had calculus. And so by looking at this, what is L? L is I omega. So we have the angular momentum. Now again, I don't have got to play a little sloppy here with the vector. So again, the L is the vector cross product of r and p. So it points in the orthogonal direction to both the radius and the momentum, and also the plane of rotation. All right, well, let's work a problem that involves conservation of angular momentum in order to solve it. So let's imagine we've got this crazy system here where this bottom plate, 3 kilograms, 15 centimeter radius, and is turning at 15 revolutions per second. And then there's this rod attached to it, and it goes up through a hole in this top piece, which is 5 kilograms and a radius of 9 centimeters, but it's not spinning. So this is spinning underneath this, and so the top is just spinning like this. And then we're going to drop this. It's going to land on the bottom disk, and we'll assume that there's perfect friction there. So it'll land on the bottom disk and start rotating with the disk. So we want to see what is the final rotation of that system. And it's a hard problem if it wasn't for conservation of angular momentum. Okay, now we're going to need a few things. We mentioned in an earlier video that when we have non-point masses, so we have like a sphere or a disk in this case, we have to look up the formula for the moment of inertia. And for the case of a disk, it's 1/2 m, the mass of the disk, times the radius of the disk squared. And so there should be a table, there definitely a table in whatever general chemistry book you're using that has these values or these formula. So you can find that for a disk. Now let's go ahead and calculate those moments of inertia for each of the disks. So 1/2 times the masses times the radiuses squared. So there's the two radius right there and there. And so that gives us 0.039 and 0.02 for the moment of inertia. We could work in radians and revolutions per second, that's no problem, but oftentimes we want to connect this to the actual omega, which is in radians per second. So if we simply multiply by 2 pi, that will give us radians per second. And now here it is, right here. This is the conservation of angular momentum statement, that the angular momentum of disk 1 and disk 2 must equal the angular momentum of the whole contraption after this has fallen onto the disk. So let's write the left-hand side. So here's L1, and then here's L2, and that's 0 because it's not moving, so there's no angular momentum there. And then L12 is going to be the total mass. So now the mass is, or not mass, moment of inertia. Now the moment of inertia just adds, and then that will be being multiplied by the angular velocity. So we can solve the right-hand side to get 3.67. We can just add these two together and then solve for omega 1, 2. And we get 61.95 radians per second, and that is 9.9 revolutions per second. Okay. So this is one problem with angular momentum. I encourage you to work through the problems in your physics book, and we'll probably have some homework problems here too, that you can get more practice with this. We're not going to talk as much about it here in the lectures, but important to get it down, and you can get it down by practicing these types of problems.